Have you ever seriously wondered how a machine actually learns from its mistakes? Well, the answer is this really cool, surprisingly simple idea called gradient descent. Just picture a ball rolling down a hill, always trying to find the lowest point. That simple motion, that's the engine behind some of the most powerful AI we have today. It really does feel like magic, doesn't it? I mean, when an AI learns to spot a cat in a picture or predict tomorrow's stock prices, what is actually going on in there? It's definitely not a ghost in the machine, it's math. And right at the very heart of that math is one incredibly elegant algorithm.
And that algorithm is gradient descent. It's been called the backbone of the learning process, and for a really good reason. It's the engine humming away inside pretty much everything, from simple statistical models to these massive neural networks. You can kind of think of it like a universal translator, one that turns mistakes into actual progress.
So, let's pop the hood and see how this engine of learning really works. How does it take a model from knowing absolutely nothing to making scarily accurate predictions? Okay, so every model starts out by just making a guess. And to figure out if that guess is any good, it calculates something called a cost function. You can just think of it as a score for how wrong it was. A really high cost means a terrible guess. A low cost means it's getting warm. So the entire goal of learning becomes super simple. Get that cost, that error score, as close to zero as you possibly can. Right, so how does it do that? If the model is essentially flying blind, how does it know which direction to go to find that lowest error? It can't see the whole picture at once. Instead, it has to feel its way forward, one tiny little step at a time. And this is where the classic analogy for gradient descent comes into play. To find that lowest point, just imagine you're standing blindfolded on a giant hilly landscape. Your only job? Find the very bottom of the deepest valley around. This, right here, is gradient descent in a nutshell. You start somewhere on that hill. First, you just feel the ground right under your feet to figure out the slope. Which way is down? Then you take one small step in the steepest downhill direction you can find. And that's it. You just repeat that simple process. Find the slope, take a step. Find the slope, take a step. Over and over and over again until you literally can't go any lower. You've found the bottom of the valley. You've minimized the error. So that's the big idea. But what does taking a step actually mean inside the computer? Let's take a look at the actual rulebook the algorithm follows. What is it really changing with each one of those downhill steps? The answer is it's adjusting parameters. You'll also hear them called weights and biases. The best way to think of them is like thousands of tiny little dials or knobs on the learning machine. Each one of those downhill steps is just a small turn of these dials, always trying to nudge that error score a little bit lower. Gradient descent is simply the process of figuring out which dials to turn and by how much.
And this single formula, this is the whole game. It's the golden rule. All it's saying is that the new setting for any dial is just the old setting minus a small fraction of the gradient. That gradient part, that's the slope we just talked about, the steepness of the hill. And that little gamma symbol, that's our learning rate. It controls how big of a step we take. That's it. That's the entire instruction manual for how to learn.
And what is so incredible is how crazy versatile this one simple rule is. For something like linear regression, it's trying to find the best fit line by minimizing one kind of error. For logistic regression, it's trying to draw a perfect decision boundary by minimizing a totally different kind of error. For support vector machines, a different goal and a different error metric again. The problems are different, the data's different, but the core engine doing the work, that's always gradient descent.
But as powerful as that engine is, it's not exactly one size fits all. To get it to work in the real world, you have to do some really careful tuning. And this brings us to the practical and sometimes really tricky choices that every data scientist has to make. Hey, remember that little gamma symbol from our golden rule? That's the learning rate. It's this number that you have to pick before you even start training. And it controls how big each of those downhill steps is. And let me tell you, getting this number right is one of the most critical parts of the whole shebang.
This is basically the Goldilocks problem of machine learning. If your learning rate, your step size is too small, the model learns so slowly. It's
agonizing, and it might get stuck on a tiny little dip in the landscape thinking it's hit the bottom. But if your step size is too big, it'll just completely overshoot the valley floor, bouncing from one side to the other wildly. It might never find the minimum at all. It has to be just right.
So the next choice is, how much data do you look at before you take a step? The first approach, batch gradient descent, is kind of like the careful student. It studies all of the data, every single piece, before taking one single precise step. It's super stable, but oh my gosh, is it slow. On the other end of the spectrum is stochastic gradient descent, or SGD. This one's the impulsive one. It just glances at one single example from the data, and boom, it takes a step. It is incredibly fast, but its path down the hill is, well, it's noisy and erratic. So naturally, people wanted the best of both worlds, and that led to some much smarter variants. Mini batch is the happy medium. It uses a small, manageable batch of data for each step. Then you have momentum, which helps the algorithm build up speed, kind of like a ball rolling downhill so it can just blast past little bumps and not get stuck. And then there's Atom, which is one of the most popular choices out there today. Atom is the ultimate tuner. It's smart enough to adaptively change the learning rate for every single parameter all by itself.
Okay, so let's put all the cards on the table. Gradient descent is incredibly powerful for sure, but it's not perfect. It's really key to understand both its strengths and its weaknesses.
On the one hand, it's super effective, it can scale to enormous datasets, and it's flexible. That's why you see it everywhere. But on the other hand, it is so sensitive to that learning rate we talked about. And maybe worse, it can get trapped. It might find the bottom of a small valley and think, great, my job is done, never realizing that the deepest valley, the actual best answer, was just over the next hill. That's what we call getting stuck in a local minimum.
And that leaves us with one last pretty crucial question. We've seen this methodical, step-by-step way a machine learns from its mistakes. But what happens when that process is tuned wrong? What does it mean when it gets stuck in the wrong valley, or when its steps are too big and it just leaps right over the correct answer? If this is really how a machine learns, then understanding this process is the first step to understanding why sometimes its learning can go so profoundly wrong.